To conclude this video series on two-factor studies with a quantitative response variable, I would like to walk you through one more example. We're going to analyze the anger data, and here is the description and coding for the anger data. The participants were 78 Rice University undergraduates ages 17 to 23. Of these 78 participants, 48 were females, 30 were males, 25 were athletes, and 53 were non-athletes. Let me stop there a moment and point out, note the unequal sample sizes here. That's why I'm showing you this example. People who did not play a varsity or club sport were considered non-athletes. The 13 contact sport athletes played soccer, football, rugby, or basketball, and the 12 non-contact sport athletes participated in ultimate frisbee, baseball, tennis, swimming, volleyball, crew, or dance. Participants were asked to respond to a questionnaire that asked about what they do to improve their mood when angry or furious. Then they filled out a demographics questionnaire. If you look at the primary variables of interest here, you will see 1, 2, 3, 4, 5, 6, 7 variables listed right over here, but we're only going to focus on 4 of them. The 2 explanatory variables are going to be sports and gender. These are factors. Sports is classified into athletes and non-athletes, coded as 1 or 2, and gender is classified into males and females, also coded as 1 or 2. The response variable is going to be this last one, anger expression. Notice that it is actually a composite of these other variables, a summing of anger minus control, that is controlling anger. And then in order to put it at a certain baseline, for some reason they add 48. So those are the 3 variables of interest, 2 explanatory, sports and gender, 1 response variable, which is quantitative, and that's anger expression. Let me go ahead and call up an RStudio notebook here. The first thing I'm going to do is read in the data. I've already converted it from Excel to an CSV file, and I'm going to set factors in the process. So my factors are going to be male and female, athlete and non-athlete. Let me go ahead and read that in, and you see here that we now have our anger data is included. If I go ahead and look at that data, the 2 explanatory variables now you can see are factors, and they're listed out as male, female, athlete, non-athlete. The anger expression, which is this last column, is going to be our response variable. I'm going to start with side-by-side box plots. So let's take a look at those. If we look at those side-by-side box plots, what I notice is that these first 2 boxes are lower than these last 2. Notice the first 2 boxes are for athletes. So the anger expression score is actually lower for athletes than it is for non-athletes. Perhaps it's the case that athletic competition leads to the possibility of anger that one learns to control with more practice. I don't know. This is not my field. I'm just making up a possible theoretical explanation. But in any case, we notice that for both males and females, the athletes have typically, not always, note we have some values up here near the top, but typically have lower anger expression scores than those over here that are non-athletes. It doesn't look to me like there's much difference between male and female. If we look both at athlete and at non-athlete, pretty similar patterns for male and female. If we want to drill down further, we can create some summary statistics here. And so here I have values for the mean for this one is males, and down here for females. If I go ahead and knit this, which I'll do now, we can actually look at this table in a little bit better format. There it is right here. So here I have the box plots, and here are the statistics that go with those box plots. And I've also added mean and standard deviation, which are not displayed in the box plots, but we're going to need in order to be able to look at mean differences. So we can see indeed that for the athletes, where we have a mean of 32 for males and 30 for females, pretty similar to each other. And for non-athletes, we see a mean of 40 and a mean also, when we round here, of 40. Again, very similar to each other, but I do notice that athlete and non-athlete are about 9 to 10 points different if we look at those. So about a 9-point difference between athletes and non-athletes, very little difference between male and female. So then I did an interaction plot using these commands that we learned earlier in the video series. Let's go ahead and take a look at that as it's rendered here once I knit it. And the interaction plot, no surprise, doesn't look to be a lot of interaction. Why not? Because the male and female scores are very similar for athlete and non-athlete. So it doesn't seem to matter whether it's an athlete or a non-athlete. The difference between male and female, male has slightly higher anger scores, but just slightly higher, and it doesn't matter whether it's athlete or non-athlete. So if I ask the question, who has higher anger scores, male or female, you would say male has slightly higher anger scores. You would not say it depends. If you said it depends on whether it's athlete or non-athlete, then you're indicating an interaction. But you really don't need to say that here, because there's very little change between athletes and non-athletes in terms of the difference of male and female. Athlete and non-athlete, on the other hand, we do see a difference. But again, would it be reasonable to collapse male and female together and just look at athlete versus non-athlete regardless of gender? Yes, it would. The values here we could collapse would be pretty much the same thing as they are separately, and the same up here for non-athletes if we collapse those values. So once I've done that, I'm now going to look at the analysis of variance. So remember, I created a model back up here in order to create the box plots. There's my model in which I'm looking, that's not model, that's the subset. Here's my model in which I'm looking at anger expression as a function of gender and sports. Because I put gender by sports interaction, the main effects are going to be included as well. So when I look at this, no surprise, I have a p-value of 0.855 for the interaction, an f-value almost 0. There is really no interaction that can be inferred because, in fact, we're not seeing any interaction in the sample, or at least very, very little. Trivial amounts of interaction. So we're certainly not going to infer something to the population that we don't even see in the sample. So knowing that I don't have much interaction, let's look at the main effects. It looks like there is a main effect for sports, that is athlete versus non-athlete, and not a main effect for gender. And that's consistent again with what we're seeing up here in this plot. Doesn't look to be any any main effects for gender. Doesn't look like male and female are much different than each other, but it does look like athlete is different than non-athlete. So that's why we're getting F values here of 0 for gender and 8.7 with a p-value of 0.004 for sports, meaning we can actually infer. Now, we could look at those means and talk about what's happening in the sample, but I've moved now to looking, can I infer what I see here in the sample? That is, that there's a difference between athlete and non-athlete in terms of anger expression. Can I infer that to the population? And the answer seems to be yes. But wait a minute. Notice what I did next. After I ran that particular analysis, which I did right down here, I changed it. And this time, all I did was create a second model by switching the order in which I put in gender and sports, now putting in sports and gender. If you remember back up here at the first one, I put in gender first and then sports. Now I'm going to put in sports and then gender. And let's see what happened when we did that. When we put in sports and then gender, we got this second analysis of variance table. The interaction still has an identical p-value to what it did above. The p-value for sports is close, but not quite the same as what it was above. And the p-value for gender has changed quite a bit. It still tells us we cannot infer, so the results of this table are the same. But up here, we went from a 0.93 to down here a 0.75. What's with that? We don't want our p statistics to be jumping around just because we changed the order. Well, the reason that this happens is because we have an unbalanced design. What I did here is I used the table command in order to see what the frequencies are. And if you look at the frequencies, you see what we read in the description of the data, that there's 11 male athletes and 19 non-athletes, 14 female athletes, and 34 non-athletes. This is known as an unbalanced design. Why am I bringing this up for the first time now? Because it's the first time we've had to worry about it. When you have only a single factor, it doesn't matter if you have equal or unequal cell sizes. It doesn't matter if you have equal numbers of individuals in each group. It's not going to change your analysis. But when you do have unequal numbers in each group, when you have a two-factor or more, that is a two-factor design or even more complex with more factors, then you have to consider whether you have balance or unbalanced, and if you have an unbalanced design, what can happen as a result of that, and what usually will happen, is that the order in which you enter the variables here will make a difference. So we have to know, how are we to approach that? Because we don't want to be choosing different p-values on the basis of different orderings. So the interaction in this case is going to be the same, and that's not just coincidence, that's always true. So we don't have to worry about the order in terms of interaction. So if we had put in either order and found that there had been an interaction, we would have been good to go. We would have moved on to either proclaiming our omnibus results or maybe doing tetrad contrast. Now, if we did tetrad contrast and did not have equal sample sizes, the formula I gave you for contrast takes into account unequal sample sizes, although it would be worth looking at an example, which I'm not going to do here, because all I do in this video and in this course is introduce you to the issue with unbalanced design. In my more advanced courses, I do the more complex tetrad contrast with unequal sample sizes, and I talk in much more detail about how to deal with the unequal sample size and an unbalanced design in two-factor studies, and in fact even in more complex studies. So this is just a brief little introduction. We're only going to look at the omnibus test. So again, if we were doing interaction and we had found that there was interaction, you know what to do. You might not know what to do with tetrad contrast, although you could follow my formula and do those, but you may not know how to deal with those. You can deal with the omnibus. You could say, I am able to reject the null hypothesis about all the tetrad contrasts being the same. That is, we have no interaction, and therefore, as a result of all those contrasts being zero and no interaction, I can say in my population with a small p-value that I infer that to the population. But what do we do in the case like this, where we don't have interaction? Well, as I've discussed earlier, when we don't have interaction, we go ahead and do main effects in the usual way. But what has been introduced now as a little bit of a problem is that we have different p-values for the exact same main effects. So what do? Well, because there's little interaction, the very first thing that I'm going to do is remove it. So notice now I've taken out interaction and instead only put in the main effects. Now I've done it two ways here, and we're going to compare those. This way I put in gender first. This way I put in sports first. So let's look at those final two analysis of variance table. Here's the one with gender in first, and here's the one with sports in first. What you are getting when you put in these factors is you are getting the sums of squares for the second factor after removing the first. So it's just as we learned for every video in which we looked at multiple linear regression, that what you're looking at is the effect of a variable after removing the effect of the other variable. In this case, though, we have to worry about, when we have factors, we have to worry about the order of the variables. And the order here is gender first and then sports. Well, which one do I need to look at? The answer is, what did you do when you did multiple linear regression? You looked at the value of a variable after accounting for the others. Gender, that's not happening. Gender is not looking here. That sums of squares is not for gender after removing sports because it's an order effect. When we put gender in first, you only see gender, but when you put sports in second, now you're looking at sports after already accounting for gender. So this is the correct p-value here for sports, but it is not the correct p-value for gender for making inferences. You might say, well, what if I, though, wanted to look at sports without gender even involved in it? Well, then you should be doing a one-factor analysis of variance. The fact that you're looking at two main effects, you need to look at what one main effect is after controlling for the other main effect. And that's what we're doing here for sports. So when we come to this second ANOVA table, it is not redundant. This second ANOVA table, the sports we're looking at here is without removing gender, but down here we can see gender after accounting for sports. So here you're looking at gender after accounting for sports, and notice it's a smaller p-value because we've accounted for sports. That is the correct p-statistic for looking at gender. Because you put sports in the model, you want to control for sports when you look at gender. Why didn't we have to do that earlier in this video series? Because we had a balanced design. If you go back to the examples that we worked out, the tooth example that I provided for you, if you were to go back to that, where we had 10 guinea pigs in each cell, and you were to switch the order of the factors, you would get the same results either way. There is no influencing of one factor on another in a balanced design, but in an unbalanced design, there is. And so that's the difference that I wanted to show you in this video. What would my final conclusions here be? My final conclusion would be is I do not have interaction in this study. I can infer that there is a difference here between athlete and non-athlete, and if I want to make that inference and report a p-value, I'm going to report this one that is 0.00399, or about 0.004. That's the one that I'm going to report. In terms of gender, I would say I do not have much evidence of a difference, and indeed I'm not able to infer. And if you wanted to report the p-value for not making your inference, you would report 0.745. So I really have to run both ANOVA tables in order to get out the correct sums of squares when controlling for the other condition and the correct p-value that goes with that. You don't have to do that for interaction. but you do have to do that for each of the main effects. Now, why does R not provide you each of these P statistics after controlling for the other variables, just like you were able to do for multiple linear regression? Why doesn't it do that for factors? Answer, it does in additional packages. There are packages available that we could use that would actually do this in one step. It would get us the correct p-values for all of the factors that we're interested in. But I do not use additional packages other than the here library in this class and in this video series. And so that's something I would introduce you to if you took a more advanced course from me. So right now, we're just going to run those two ANOVA tables. And indeed, all I'm doing is giving you one video to introduce the concepts to you so you can be aware when you leave this class that if you have unequal cell numbers in each of your conditions, that you don't want to just rush in and do a two-factor ANOVA without taking into account the fact that you have an unbalanced design. This concludes this video series. I hope you feel as though you learned quite a bit. And you certainly learned also that there's much more to learn if you were to move on in terms of more advanced techniques, more advanced R packages, more advanced contrast. But in terms of the basics of two-factor analysis of variance or two-factor studies with multiple linear regression, I hope you believe that you have learned much, as I think you have.